So let us look at a few applications of Fermi-Dirac statistics. Now we know that the thermodynamic properties of any fermionic system, it can be computed if we know about the single particle energy and the expression for the density of the states. So if we know these two things, we can compute the thermodynamic properties of any fermionic systems. So the first application of Fermi-Dirac statistics is in the context of astrophysics. And this is probably one of the first applications of Fermi-Dirac statistics so it dates back to 1926, and the scientist by the name Fowler. So he proposed that the relationship between the density, energy, and temperature, so it can be explained by viewing the white dwarf star as an ideal non-relativistic gas of electrons and nuclei that obey Fermi-Dirac statistics. The second application of Fermi-Dirac statistics finds application in the field of nuclear physics. So there is this famous Thomas Fermi model. Now this is used as an approximation technique nowadays, and it is even used for both systems. So this was an application of Fermi-Dirac statistics. So the other application is for calculating the binding energy of nucleons. And we know that this can be useful in a variety of applications, the binding energy of nucleons. So these are the two ways in which Fermi-Dirac statistics is useful in the field of nuclear physics. So another application of Fermi-Dirac statistics is in the field of solid state physics. So now Pauli could explain the weak temperature dependence of paramagnetic susceptibility of metals that were exposed to weak magnetic field, and this explanation was compatible with the existing experimental observations, and it confirmed that conduction electrons do obey Fermi-Dirac statistics. So that's how magnetism and other aspects of solid state physics can be explained using Fermi-Dirac statistics. So the other notion is that of the electron gas model. And so the electron gas model is basically, it models the metal as a collection of free electrons that is confined to a three-dimensional box of volume V. Now here the single particle energies are modeled after those appropriate to a quantum mechanical particle in a periodic box of side length L. Now we find that from mathematical calculations that as T tends to 0, the pressure of the free Fermi gas it tends to a constant. Now this phenomenon could not be explained by Maxwell-Boltzmann statistics for obvious reasons, and Fermi-Dirac statistics could explain this phenomenon mathematically. So as you can see that the non-zero pressure, this is called the Pauli pressure, and it arises solely as a consequence of Pauli exclusion principle, and the bulk modulus of a metal mostly as a result of polypressure. So polypressure also resists the gravitational collapse of a white dwarf or a neutron star.